Let me check the mic is on. Because, okay, it is. Excellent. Because sometimes it doesn't, the mixer doesn't come back to record the voice. There we go. That's good. So let me give you an example here. Okay. And I think the question that I got had to do with, or it can be solved by understanding this part. So the question is, the basic distribution rule, says, something like this. Okay, I'm just picking the one that arithmetic does not have. Okay, so once again, multiplication is conjunction, addition is disjunction. So when you have a conjunction and then the outer operation is a disjunction, the inner operation is a conjunction, you can combine these two, to become A plus C, or A or C, and B or C. Okay, that's one way to use a distribution. Now this one obviously doesn't work in arithmetic, but it does work in Boolean algebra. Okay, so the question now is, okay, understanding this one, what do we do when we have AB plus CD? Okay, well, you can apply that rule twice. So what you do is you look at CD as one thing, so you have A or CD as one thing, and then you have B or CD as another thing, and then when you look at each one, then you reapply distribution again, okay, so that you can have the actual fully spelled out version after the expansion. Is that okay so far? Okay, all right. So that's just basically a technique, of, I give you all the simple rules, but by, combining the rules, okay, or reapplying the rules in a nested way, you can solve, more complicated cases where the rules themselves do not cover. So are we good so far? All right, cool. All right. Okay. So the next thing is kind of go back to discrete probability, and we're going to start with counting, which is, something that you might think, hey, I learned that, in elementary school. Do we really have to talk about this again? Well, if you look at the counting module and you look at the bottom part of it, you probably will have the idea of, yeah, maybe we should talk about it. Because we got, a nested application of a union on, things in T, and then the other one is even more nasty. Look at this one. Look at this thing here. To quote your Rush, right? Look at this. Look at this. So you have got a union on the outside, and then what you're unioning is another union. But when you look at, the subscript or the indexing operator of the union, we're taking a set out of this thing here, which looks exactly like this one, and then we take one of these things and then we make a set that is the union of these things that has one element, which is the union of the set that only has E, which is picked up from here, and S, which is picked up from here. And then so it's a nested, nested iterative union of stuff. Okay? Yep. Question?
Did you also copy this somewhere from the internet?
No. Now, this is something I was trying to figure out last semester because somebody asked me and go like, what about, combinations? Because I got one for permutations already. Somebody asked, so do you have one for combinations? So I was trying to work it out. Yes?
No, that's basically Raj saying like, oh, I copied it off somewhere off the internet.
Oh, right. That part I do not do. I only use the internet to figure out, what theorems there are that are related to this class. And then, I try to prove every single one of those myself. Which means, sometimes my proofs may not be the most optimal. It might be longer than what is necessary. All right, so we'll go from the beginning. Okay, you can see that even though the module is titled counting, it's not really the very simple counting. That's because we are counting. Basically, we're trying to address the counting that is needed when you try to figure out the chances of winning the lottery. Okay, so that's the kind of counting we are trying to do. All right. So there are a few terms we need to first understand first. So these are the terms that we need to understand. So we first, we start with a trial. A trial is a single attempt to do something, typically involving choosing something. A single choice is a trial. So I'll give you an example. This is kind of abstract. So you can consider throwing a dice once as a trial. Okay? Well, what are you choosing? Well, you're choosing one of the 6 faces of a regular dice. If you play D&D, obviously you have 20 face dices, and what else do they have? In addition to 20 face, huh?
Like a D4.
4? Okay, yeah, that makes sense.
D12.
12, 10, okay. So do you use those in combinations too, sometimes?
Sometimes, yeah.
Okay, all right. So throwing a dice is definitely, an example of a trial. Flipping a coin is also a trial. Picking a number out of a basket, like in lottery, that's also a trial. Okay? So we'll distinguish the differences between throwing a dice versus picking a ball out of a basket. Okay? Because one is with replacement and the other one is without replacement. So we'll deal with that later. The next line or the next paragraph talks about a trial has possible outcomes associated with it, and each outcome represents a possible result of a trial. What does that mean? What is a possible outcome to a trial? If a trial is flipping a coin, okay, then the possible outcomes, there are 2, head or tail. Okay? Sorry?
Or it lands on its head side.
Landing on the side. Hopefully, eventually it will fall down. So hopefully the edge of the coin is curved enough that it's gonna have to fall down. If you throw a dice, okay, like a regular 6-faced dice, that's one trial. But there are 6 possible outcomes from one single trial, because you can get 1 to 6, okay, depending on how it lands. Does that make sense? So if you have a 20-faced dice, then you have one single trial has 20 possible outcomes. So are we good so far with what a trial is and how outcomes relate to a trial? We good? Okay. So now we talk about experiments. An experiment is a series of trials where subsequent trials may affect earlier ones, may be affected by earlier ones. Okay, bad grammar on my part. Okay, so this is where things some experiments can be done with replacement, and some can be done without replacement. If you think about lottery, where you pick a number out of a basket, that number is never put back into the basket for the next trial. That is without replacement. Okay? When you throw a dice, okay, that is with replacement. Because if a dice lands, and 6 is the number, well, you don't just erase 6 for the next trial, right? The next trial can also land on 6. So that's why that is with replacement. So we'll talk about that in a little bit more details later. Question?
Just
yeah?
to clarify, replacement repeats are possible?
Yes. It means whatever the choice is for an earlier trial, it can again be a trial. It can be a choice for further trials or future trials in the same experiment. So the outcome set, the set of all possible outcomes of an experiment, is usually represented by omega. So this omega is not to be confused with the omega in propositional calculus, which is the set of all the operators. So we are reusing symbols, okay, but they mean different things. We'll see omega one more time, when we talk about time complexity. So apparently omega is a very, popular symbol for mathematicians to use. All right. So let's go ahead and talk about general counting. So let's say we're counting the number of possible outcomes of an experiment. So in the case of lottery, we'll be counting the number of unique lottery tickets. Does that make sense? Okay. So there are a few symbols that we are going to use here. So I'm going to use the symbol T with a subscript of I to represent the outcome set of trial I. Remember, an experiment is a series of trials. Okay, so Ti is representing the outcome set of trial I, or the ith trial. So we start with 0. Okay, that's the important part. So it's 0 oriented. In this case, Ti does not influence Tij, Tj, where j is greater than I. So this is with replacement. Actually, I take it back. So this has nothing to do with whether it is with or without replacement. It just means that we are not influencing the chances or the chances of the outcomes. Yep.
So is T subscript J just a new trial? Like a trial?
It's a future trial because j is greater than I. Yep.
Would you say that rolling the same six-sided die would Ti, if that were the case, T sub I would influence T sub j because of the orientation of that die?
But you're going to throw it again.
Right.
So if you throw it again, that resets everything. Yeah. So that would not influence it. So now, if you want to look at the outcome set of an experiment of m trials, then it is a Cartesian product of all the outcome sets of each individual trial. Okay? I'll give you an example. So let's think about throwing a coin 3 times. Okay? So you have 3 trials in an experiment where each trial has 2 possible outcomes, head or tail. Does it make sense? Okay? So if I were to write it out, okay? So in this case, when we are flipping the coins, I'm going to make it clear what we are talking about here. So we basically say that 3 trials flipping coins per experiment. So in this case, T, instead of subscript 0, I'm going to use this to denote, subscript 0. So T0 is going to be, well, it's either head or tail. And then the second one, or T1, is also just, head or tail. And then in the last one, it is also just, head or tail. Does that make sense? Because, just because the coin lands on the head in the first trial doesn't mean that it cannot land on the head again in future trials. So now when you look at omega, okay, so omega is going to be T0 Cartesian product with T1, Cartesian product with T2. What do you think that set is going to look like? Yep. There are 8 of them, right? So you got HHH, HHT, HTH, HTT, THH, THT, TTH, TTT. All right. You go like, well, how can you come up with these, combinations so quickly? If you think about it, okay, if you equate H as 0 and T as 1, I'm just spelling out the first 7 binary numbers. 0, 0, 0, 0, 0, 1, and all the way to 1, 1, 1. Right? Okay? So are we good so far when we look at what a trial is, what are the outcomes of a trial, and what are the outcomes of an entire experiment, and how all of those terms relate? Yep.
So is like the experiment just one of the tuples in omega?
The experiment is
Like an experiment, would that just be one of the tuples out of omega?
an outcome of an experiment is one of the elements of omega.
Okay.
But omega itself is representing all possible outcomes of an experiment. So everything that is possible is in omega. Yep, go ahead.
I don't quite understand why you have I mean, would each element be the same?
Well, okay, first of all, I was lazy, okay? Because, technically speaking, each element is a 3 tuple, so it is supposed to be like this. But I was too lazy to draw, to write all the parentheses. Yeah. So I apologize for my laziness and neglecting to say that this is a shorthand of X in the 3 tuple. But technically speaking, X is a 3 tuple where each item inside the 3 tuple is a head. Because that's how we do Cartesian product. Okay, so are we still good so far? All right. Okay, so why do we need Cartesian product? Well, we need Cartesian product because for each element of T0, it can combine to anything in T1, which can then be combined with anything in T2. Okay, so the best way to understand why it is multiplication instead of addition is a picture. So I'm going to draw a picture, and hopefully my pen is charged because I left it somewhere on the desk and somebody collected it and put it into the drawer. So it may or may not have enough battery, so let's hope it does. Alright. Yep, that's good. It does have battery. Okay, so the best way to look at this is like this, okay? So let's say this is representing the beginning of the entire experiment, okay? And we're still talking about flipping a coin 3 times, okay? So after the first experiment, what can happen? One of 2 things can happen. You can have a head or a tail, right? So this head and tail is representing the outcome of the first trial in the experiment, okay? What about the second trial of the experiment? Well, doesn't matter, right? Even if the first trial has a head, the second experiment can also have a head or a tail. And even if the first experiment has a tail, the second trial is, I keep saying the word experiment, but the second trial can still have your head or tail as the outcomes. Is that okay? But do you start to see why it is multiplication? Because it says for each outcome of the first experiment, we can have these as the outcomes of the second experiment. Okay? So that for each is a clue to say that, well, we might be thinking about multiplication here. Okay, but just to make this diagram complete, if the first 2 trials were head-head, well, the third trial can still be a head or a tail. So we have head-tail again here. Head-tail, head-tail, head-tail. There we go. That's why it's multiplication. So sometimes a picture can really kind of help to understand why it is multiplication instead of addition. So I hope this helps you understand why in this case it is multiplication. Are we good so far? Kind of? All right. Okay, so switching back to the notes. Everything should be recorded, so let me just double check and make sure the recorder is on and the voice is there too. Okay, good. All right. So for counting purposes, okay, if you want to count the total number of outcomes for the entire experiment, and there are m trials, then it becomes the pi of I going from 0 to m minus 1, and then the cardinality of each t subscript I. Does that make sense? Yep. The big pi means multiplying all the terms together. So sigma is for summation, and this is for product. Yep.
So is that the Cartesian product in this case?
It's not. This is arithmetic multiplication, because we are already taking the cardinality of the set. So what we are doing is we look at the cardinality of T0, T1, T2, and so on, and then multiply all of them together. Do you guys know why summation is using sigma? And why multiplication is using pi? Product starts with P, and then sum starts with S. Yep. That's a quick way to remember, why they chose those particular symbols. So are we good so far? All right. Cool. So in a case where each trial has exactly the same number of outcomes as all of the other trials, then it's easy, because if n is representing the number of outcomes per trial, then n to the power of m, which is the number of trials, is going to be the total number of possible outcomes for the entire experiment. Does that make sense? I mean, flipping coins is one of those examples where n is 2, because each trial has 2 possible outcomes, And then when you're talking about experiments, like, oh, I want to look at an experiment of 5 coin flips, then M is 5. Yep.
So would that be true for any experiment that involves replacement, like if you have with replacement?
Yes.
Okay.
So throwing a dice would be the same thing.
Yeah.
So if you have a 6-faced dice and you throw it 3 times, okay, then the total number of ways, the total number of outcomes where order is important is going to be 6 to the power of 3. Now remember, order is important in these cases. Okay, so we are counting, head, tail, head differently from head, head, tail. So they're considered as 2 distinct cases. Yes?
This notation, M is referring to the amount of trials in the set.
Which
Minus
symbol?
1. So you've got big pi and then top one's M minus 1. What is M?
M is the total number of trials of the experiment,
Okay. Thank you.
which is introduced here. Yep. So are we okay so far with experiments that has replacement? Yes, go ahead.
A little earlier, yeah, every F in T1, F is just, what is F representing?
F is representing an element of T1.
Right.
So I just use F to distinguish it from the E here. So if you choose one thing out of T0, okay, what can be combined with from the second trial? Every single one of them.
Okay.
So that's basically what it's saying. Right. Any other questions? I think the best way to remember this is this one here. Okay, so when we look at the omega, okay, so I'm just gonna kind of finish this one. So when you look at the omega in this case, it's just going to be, once again, I'm using the shorthand. So H really is a 3-tuple of head, head, head. Okay, but using this shorthand, I mean, this is just a graphical representation of something that we talked about already. So there's no new information here. I'm just trying to make it so that you can see how the picture correlates with the text that we have already talked about. Is that okay? And if you really want to, okay, you can even do a little bit more and just look at these two. This is basically T0. And then this and this, they're both T1s. Okay, they're the same because it doesn't really matter. And this one is T2, so is this, and so is this. So are we good so far? Okay, kind of like a more graphical way to represent the same stuff that we have been talking about. Yes?
It's because it looks like it's close to binary tree or tree. So
It is a tree.
yeah, is it possible we calculate that like nodes of a tree like 2 power n?
That's exactly what this is. So when you look at the total number of outcomes, each outcome of the entire experiment is one leaf. So in this case, it's very easy to calculate because the number of the fan-out ratio is the same for every single level. So you just do the multiplication. Okay, and to generate the actual omega, it's pretty simple as well, because you just say, okay, for everything that can happen in the first trial, let's combine it with everything that can happen in the second trial, that can happen, and combine it with everything that can happen in the third trial. So it's relatively easy to generate it and to calculate what is the size or the number of elements in omega in this case. So are we good so far? All right. Okay. So switching back to now we go to without replacement. So a common restriction, I'm just reading the notes here. A common restriction to trials in one experiment is that whatever is chosen in an earlier trial cannot be a choice again for later trials. So that is the case with lottery, okay? It's also the case when you want to choose a vacation destination and go like, okay, where do we want to go this year? We got 6 places that we can choose from, okay? So unless you really want to go to the same place again and again, okay, most people go like, okay, we'll do it without replacement. We'll choose 3 different places to go, this year for vacation. Okay, so in this case, how do we do all the calculations? So now it's a little bit tricky. So we'll say, if E subscript 0 in T is the actual outcome of trial 0, okay, then E0 is no longer available for trial 1. So trial 1 now has an outcome set as for the trial itself of T minus in the set E0. Does that make sense? Because E0 is no longer available as a choice in the second trial or trial 1 in this particular case. Is that okay? And as a result, T minus the set of E0, the cardinality of that set is n minus 1 if n is representing the number of if n is representing the cardinality of T itself. Does that make sense? Okay, you got 6 destinations to begin with, and once you have chosen the Bahamas as the first destination for this year's vacation plan, then the Bahamas is no longer available as a choice for the second destination that you want for this year. Is that making sense? Is that okay? Okay, all right, okay. So if I use E subscript I to represent the actual outcome of trial I, then we can see that for trial I itself, the outcome set is now limited to something like this. So now is a good time to understand, what is that big U doing? What do you think?
It combines
Probably corresponds to something that's that has a word that starts with U, right? So which word do you think starts with U in this class? Union. Very good. So this is a loop, just doing all the unions of each individual term. So in this case, the index is J. J goes from 0 to I minus 1. And then each item that we're unioning is the set of EJ by itself. So we are unioning, okay, the set of E0 with the set of E1 with the set of E2, E3, all the way to the set of E subscript I minus 1. What is it going to make? It's going to make one big set, right? So the one big set is making has elements E0, E1, E2, all the way to E subscript I minus 1. That's just a programmatic way of specifying that particular set. But that is all being quote-unquote subtracted from T because those elements have been used in earlier trials already, and as a result, they are not available for trial I. So T minus this messy thing is going to be the set of possible outcomes for trial I. Yes?
To be like a specific trial?
T would be the T is the set of possible outcomes available for the first trial, or T0. Is that okay? Do we have any questions about the symbols, the meaning of the expression, or what it is representing? Okay, we don't have any questions. All right. So the cardinality is easy to figure out. Okay, so if I know the cardinality of T is n, then I know the cardinality of this mess is n minus I. Well, the reason why we know that is the cardinality of n minus I is we know each of these E originally comes from T. Okay? Now, if I can choose some E that does not come from T, I wouldn't be able to get the answer. But because the way I choose each one of these E, okay, without reading the notes here, what is each E is representing? What is EI representing? It's the choice of trial I. But that has to come from T, right? Originally. Okay? So do we have any questions about the symbols or the equation or the formula up to this point? Yep.
So for that last one, would it just be like, as an equation, the cardinality of Ti equals that whole thing?
Yep.
And then with that T is T0, right?
Yep.
Okay.
So are we good so far? Hopefully. All right. So then we look at some kind of messy mathematics here. Because we want to figure out, what exactly, what is the outcome of this whole thing. So, first of all, why am I interested in this thing here? Okay, forget about this, just look at the big pi and the index. Have we seen that before? Big pi, where the index I goes from 0 to m minus 1, where m is the number of trials in the experiment. Yeah, we talked about it about 5 minutes ago. And what was it about? Why is that important?
For omega, it's the cardinality.
It's for calculating the total number of outcomes in omega. Okay? So what about this part here? Why do you think n minus I is important? N minus I is representing the number of choices for trial I. Okay? It was a very simple n before, where we had with replacement, but now that we are without replacement, you have to remember, for trial I, it has fewer choices than the earlier trials. Is that okay? So that was the only change from before. But we want to come up with a closed form of this. In other words, we look at this equation and go like, well, that looks kind of messy. Can we make it look nicer? Okay. So this equality here, what did I do with this equality, the first line? How did I mean, it looks really complicated, but the idea is really simple. It's multiplication by 1. Yep. See how this and this are exactly the same. But the trick is, how do these relate to this thing here? Okay, so
They start one after.
exactly. See how in the outside pi, it is ending with m minus 1 as the index. Okay? But when you look at these two, they start with m and they end with n minus 1. Is that okay? So that was intentional. It was intentional because now when you look at this one and this one over here, okay? So when you look at this pi and this pi here, they connect. They can become one bigger pi over here. You cannot do that to actual pies. But with this, product, you can. Okay, so I can see some people are not, connecting why that is the case. How we got from the first line to the second line. So on the first line, we have this pi going from I is going from 0 to m minus 1. And then we have this pi going where I goes from m to n minus 1. And n is greater than m. Okay? So do you see how this is the continuation of that? Is that okay? So that's how we can end up with multiplying this with that, we end up with this. Is that okay? Hopefully? Okay. And how did I go from the second line to the third line? What trick did I use so that I can shift things around a little bit?
Combine the top two.
The top two are already combined. So this and this combines to this. So how did I go from the second line to the third line? What got changed? Yep. I shift things around a little bit, right? Okay, so when you look at this pi here, okay, when I equals to 0, n minus I is going to be n, right? When I is n minus 1, then n minus the whole thing, okay, n minus 1, is going to be 1. Is that okay? So that means what are we multiplying in the numerator of this fraction? We are really just multiplying 1 all the way to n. Okay, let's rewrite it in a very simple form where I just go from 1 to n, and I is the term that we're multiplying. Is that okay? So that's the explanation of the numerator part. What about the denominator? So when you look at the denominator of this guy here, the first term that we're going to multiply with the denominator is n minus, and then in parentheses, m. So it's n minus m. And the last term is still a 1, because n minus, in parentheses, n minus 1 is really just 1. So what we're really doing is I is really just iterating from 1 to n minus n. Is that okay? So I'm just playing a trick, okay? I'm playing a trick by changing the index and also changing the expression so that we are still dealing with the same terms, except they're spelled out differently. Is that okay? So when you look at the top term, okay, so getting to we're trying to go from the third line to the fourth line now. So on the third line, we basically are saying, oh, this is really just 1 times 2 times 3 all the way to n. And the bottom one is 1 times 2 times 3 all the way to n minus m. But each one is now just a factorial. So now we end up with n factorial divided by n minus m, the whole thing factorial. Is that okay? Do we have any questions about the derivation here? Yep.
So like the second and third line, you just shift some indexes
Yep.
to get there, and then the last one you just carry out the cancellation for the division.
The third one, so between this and this, I use the trick of playing with indexes and changing the expression of what we are dealing with in each term. And then from here to here is just, oh, we know how to call this and we know how to call that. Those are all factorials.
Okay.
So we just make use of the definition of factorial and say that, well, instead of using the pi symbol, we now have a simpler way to refer to it. So the conclusion of all of this derivation is really just oh, okay, there's a special term for this particular expression. It is the number of permutations when you're choosing m items from n. And n has to be greater than or equal to m. Let me say that one more time, okay? This is known as the number of permutations, and that's why we use the word p here, the letter p. So it can be expressed with n, which is the number of choices for the first trial, as a superscript, and then m, which is the number of trials for each experiment, as a suffix, not suffix, superscript, subscript. There you go. So n is the superscript, m is the subscript, or you can also parameterize it like that. And it tells you the number of permutations when you need to choose m things from n things. Okay, what does that mean? I mean, let's think about this a little bit more. Okay, so once again, let's talk about vacation plans. Okay, so at the beginning of a year, okay, you say, okay, you gather all the people that you want to go traveling with, and you say, okay, what are our options here? Okay, let's think about your possible destinations. Let's say, as a group, you guys came up with 12 different destinations. Okay, and each one of you look at your bank statement and go like, can't do that. We can do 3 of those, but we cannot do all 12 of those. Okay, so then you guys have to say, okay, let's put the 12 destinations onto paper. Crumple the paper, throw it into a hat. Okay, and you just say, okay, shake the hat a little bit. Okay, and say, okay, let's see which one is going to be our first destination this year. Go to the box, unravel the paper, and go like, the Bahamas. Great. Okay, so now you have your first destination of the vacation plans, right? Then you go to the hat, okay, pick out the next ball, wrinkled paper, unfold it, and go like the Sequoia National Park. Okay, that's your second destination. And then now for your last destination, go into the whole mix, pick out a piece of paper, unravel it, go like Las Vegas. Okay, nobody's getting the I choose Las Vegas because we are dealing with chances and probability and stuff like that. Okay, anyway, I should have chosen Monte Carlo and Macau for the other two destinations because both of those are well known for gambling and casinos. Anyway, so you have all three destinations now, right? But the order is important because we have to go to the Bahamas first, okay? That was the rule, okay? Whatever we chose first is the first destination. Is that okay? All right. So yeah, go ahead.
Calculating the number of permutations, though, that, I mean, thinking about order when we're just calculating the number of permutations is not relevant, right? Knowing which.
Okay, so the question is, when do you think the ordering is important
Yes.
and when is it not important,
Yeah,
right?
that's right.
Okay. So in the case of choosing vacation spots, I think the ordering is important. Okay. Unless the group decides it is not important. I mean, you can choose either way in that case. Okay. Let's deal with the birthday question, birthday problem. Okay, where permutation is actually important. Okay, so we're going to switch gear here a little bit. So we're switching gear and we'll try to answer this question here. Okay, with a class of n students. What are the chances that no one, and how should I put it? Okay, that everyone has a unique birthday. Okay, that's the question. Okay. So let's say we have a class of 50, okay, in cisp440. So the question is really asking, what are the chances, okay, in percentage as a ratio, that everybody has a different birthday in the entire class of 50 students? So how would you try to figure that problem out?
Maybe it's none.
Huh?
It's none.
So the question is really asking, so there are two ways to look at this. The best way to look at this is basically to say, okay, in a big box, okay, you have 365 days, okay, and then you're asking how many ways can we have this entire class of 50 people to pick out these little numbers from the box. Let me say that one more time, okay? So now I'm changing the problem a little bit. I'm looking at the problem in a different way. I'm looking at the problem now as, here's a box, 365 items in the box. They're all unique. So each person in the class will just come around here and take one item out of the box. But do not put it back into the box. It is without replacement. Is that okay? And my question is, how many ways can we do this? 365 items, choose 50. Now, the question now is ordering important? It is important, okay? Because you should not count me choosing April Fool's Day and you choosing the New Year Day and the other way around as the same thing. They are two different ways of picking items. So ordering is important. Okay. So now we can say, so we got 365 and we're choosing n out of 350s. So there are this many ways to choose unique birth dates in this class. But that's just counting. That doesn't give us the probability, right? So what about the probability? When you're talking about probability, you're basically looking at this particular count and you divide it by the total number of ways for the entire class of 50 to choose their birthdays. So what would that be? Okay? So let's say the first person, chose April Fool's Day. Okay, April 1st. Okay? Is it possible for the second person to also have the same birthday? Yes, it is.
Wait. If you're saying there's no replacement, right?
No. The count that we're interested in is without replacement. Because what we're interested in is to figure out the probability of no two people in the class share the same birthday. So that's what we're interested in. So when we're counting that, it is without replacement, and that's why we use permutation. Yep.
So do we go back to like that n to the m formula we had earlier?
Yes, exactly. So in this particular case, the omega, or the cardinality of omega, is 365 to the power of n. Because the first person has 365 days to choose from. Guess what? The second person also has 365 days to choose from. Because we are looking at all the possible ways for a class of 50 people to have their birthdays arranged with no restrictions. Is that okay? Alright. So this is the total number of ways to assign birth dates without any type of restrictions. Alright, so what do you think is the probability? This is the number of ways to get what we are interested in. This is the total number of ways without restriction. What do you think is going to be the chance? One over the other one. Okay? So now the probability, okay, of each person in a class of n students having a unique birth date is, it's just a division. So now we are looking at P 365n divided by 365 to the power of n. Are we good so far? Does that make sense? So, okay. Let me just use a symbol here, because instead of saying permutation of 365 choose n all the time, and power 365 to the power of n, we'll just refer to those things as x and y. Okay. X represents the number of ways to do things that I'm interested in. Y is representing the total number of ways to arrange things, including the ones that I'm not interested in. So the probability of getting something that I'm interested in is going to be x divided by y. Is that okay? Yep.
So
Yes. So y, yes. Yeah, because in reality, people can have the same birthday. But I'm interested in, okay, what are the chances that no one shares the same birthday? So the math is like this, okay? The math is kind of abstract, though, like, oh, okay, we are just dividing a permutation by a power, okay? But what do you think it looks like? Like in a class of 50, what are the actual chances that no one in this entire class shares a birthday with anyone else? You guys want to take a look? Okay? And the best way to do this is, as usual, a spreadsheet. I use a spreadsheet for everything. Yeah, that's leftover note from a meeting that I was in. It's kind of interesting. I'm not sure how much of this you guys want to know. Cybersecurity pathway and cybersecurity programs. Okay, so as it turns out, as a region, there's an interest to develop cybersecurity certificates, and we might get funding for a region-wide program to do that. But to do that as a region program, it cannot be just an ARC thing. It has to be ARC combined with at least one of the other sister campuses. So that's what that's what's involved here. What is involved here? The second one, the second paragraph is also kind of interesting. The state of California has a lot of retirement coming up. They know, because they know the age of employees, and they can see there's a big exodus because of retirement. And many of those are the people who used to run the IBM mainframes and develop code for the mainframes and stuff like that. And because there's a huge exodus, that is expected to happen, and they know the incoming stream of employees is not going to meet that requirement. So the state of California, IBM, which is their main vendor of IT stuff, now want to kind of partner with Los Rios to have classes so that we can help prepare entry employees to get back into their IT jobs. So that's kind of interesting. Yep.
For the permutations that we were looking at, is it P365N or PN365? For the one we just did.
It's choosing N out of 365.
So is it the N first or the 365 first?
I believe it's the 365 first. But we'll see, because we'll open that document right now. So we're looking at a new spreadsheet. By the way, this works in a Google Sheet as well, so if you guys want to try Google Sheet, that works too. So we have 1 as the N here, and then we have the second one is just going to be the previous row plus 1. And I will show each one, individually. So permutations. So this is going to be permute the total number of elements, which is 365, and then N is representing how many we're choosing from. So we got 365, and then we have the total, or this is the cardinality of omega, and that is 365 to the power of the number of people in the class. Okay, does that make sense? If I have one person in the class, okay, there's only one way. There are 365 ways to assign a birthday without replacement. Does that make sense? If there's only one person, with or without replacement, doesn't really matter, because there's no second trial to speak of. Okay, so that seems to make sense. Now, because I use a spreadsheet, things are getting a lot easier. With 2 people in class, the numbers show up like that. Okay. And we are looking at the ratio, so this is the probability. So the probability is this number divided by that number. Okay. Does that seem to make sense to you? There's a 99.7% of a chance that if you have 2 people, that they will have unique birthdays. It's very likely that when you have 2 people, that they will have unique birthdays, right? Okay. So it makes sense, okay? Because we want to make sure that things actually make sense, for the extreme cases. When you have only one person, you have 100% chance that that person does not share the birthday with anybody else. Does that make sense?
Yes.
Okay. So we'll work out these numbers, okay? So this is why I like spreadsheets, because not only can I plug in numbers and quickly come up with a result, but I can actually look at the trend of things, okay? So you can, just focus on the first column and the last column, okay? The ones in the ones in the middle can get pretty big, so they can get pretty difficult to read. When we have 18 students in the class, we only got like 65.3% of a chance that no one in the class shares a birthday with anyone else. 60-something%, but that's only with 18 students. Okay, so we want to figure out what if we have 50 students, right? So we just have to get it down to like row 51. So with 50 students, it's a pretty low chance. We have 2.9 or 3% of a chance that no one shares a birthday with another student in the class. That's with 50 students. It doesn't seem to make sense, right? Because you think about it, go like, well, 50 is like 1/6 of, 1/7, less than 1/7 of 365. But the chances of, having everybody having a unique birthday is only like less than 3%, just a little bit less than 3%. It's kind of cool, okay? But remember, the reason why we came up with this example is to illustrate why permutation is important, why ordering is important. Is that okay? All right. So getting back to the notes here, okay. So this part only talks about ordering. It's like given a certain number of items, okay. So here's a basket, okay, a box. There are 5 items in a box, okay, and this is how some companies make new products, okay. So they throw in some ingredients into a box and say, how many ways can we rearrange these items? Okay. Well, so in that case, you have 5 items, and you're choosing all 5. So you're looking at a permutation of 5, choose 5. Well, what is that going to look like? So if we scroll down here, we can see that when you're looking at the number of ways to choose m items out of m items, then you have m factorial ways to arrange those things. They're m factorial permutations, which kind of makes sense, right? You have 5 items in the box. The first person has 5 choices. The second person has 4 choices, 3 choices, 2 choices. Don't have a choice. There's only one thing left. 5 times 4 times 3 times 2 times 1 is 5 factorial. Okay? So, when you want to look at the number of combinations where ordering is not important, you basically, all you have to do is to get rid of the duplicates. Okay? So P and M is already telling you how many permutations we can have, choosing M from N items. And all we have to do is to say, oh, there are M factorial ways to arrange M items, so there are M factorial quote-unquote duplicate items when we only look at the permutations. So the division will give you the actual number of ways to get the combinations. So in a combination, ordering is not important. Okay? In a permutation, ordering is important. Is that okay? So when you do all this math here and just kind of manipulate things around a little bit, then the combination of the number of ways to get combinations choosing m from n is n factorial divided by m factorial times n minus m factorial. You can find the definitions, like on Wikipedia, pretty easily. But what I want to do is to explain why the equation is the way it is. Are we doing okay so far with all this math stuff? Okay? So when do we not care about ordering? Since when do we care about only combinations and not permutations? Lotto tickets. When you buy lottery tickets, ordering does not matter. You can buy a ticket and you handwrite 5, 4, 3, 2, 1. Well, guess what? It really is the same thing as writing 1, 2, 3, 4, 5, or writing 1, 4, 3, 2, 4, and so on. The ordering is not important. It's basically considered as a set. Okay? The only thing you really care is this number one of your chosen numbers? If it is, it's good. Okay? Is it your first chosen number? Who cares? Is that okay? Okay, so that's when we need to know combinations instead of permutations. So let's take a step back, okay, and think about all of those things that we have just talked about. The first one is with replacement, okay. So if we're dealing with replacement, then the number of permutations is easy to compute. It is n to the power of m, where n is the number of possible outcomes per trial, which stays the same for all trials, and then n is the number of trials per experiment. Excuse me, m is the number of trials per experiment, so the number is n to the power of m. As an example, you have a dice that has 6 faces. You throw it 3 times. Okay, so the total number of how the numbers can come out where ordering is important is 6 to the power of 3. Is that okay? Are we good? Second question. Okay, what if we are dealing with something that is without replacement, like counting the number of ways that a class of 50 people can have unique birthdays. Okay, it's the same thing as having each birth date represented by an item in the box. So we got 365 items in the box, where each student is going to pick one item from the box. The question is, how many ways can this happen? Well, the first student of the 50 has 365 choices. The next student has 365 minus 1 choices, and then 365 minus 2 choices, and so on. So when you multiply all of those things together, it is known as the permutation. Okay, the permutation of choosing 50 out of 365. That's permutations. Then we get to combinations, where ordering is not important. Okay, which is choosing the 5 lucky numbers in the lotto. Okay, if 16 is one of the numbers that you have chosen, then it is good. Okay, it doesn't matter whether you chose 16 as your first number, second number, third, or fourth, or fifth. As long as it is on your ticket, it counts. Okay, so are we okay with those concepts? Differentiating, n to the power of m from p and m from c and m. We good so far? Are you remembering the examples? Because that the examples will help you remember in what situation which one is important. Are we good? Okay? Yeah.
So let's say you have an example of something like let's say you have like 10 ice cream flavors, okay?
10 ice cream
10 ice cream flavors.
flavors.
So the number of possible arrangements of like let's say they're all different, right? The number of possible arrangements is 10 to the n, or how would?
Okay, so with ice creams, okay, that's a good one. Okay, so with ice creams as an example, let's say you go to Baskin Robbins. Okay.
Yeah.
How many flavors do you have? 31. Very good. So you have 31 to choose from. Okay. So you can say, I'm going for a 3-scoop special. Okay. So the question is, how many ways can you get those 3 scoops out of 31 flavors? Okay. Well, if someone asks you that question, you have to ask back a question. Okay. There are 2 questions you have to ask back. The first one is, are we doing with replacement or without replacement? In other words, if I really like chocolate, can I have 3 scoops of chocolate? Does that count as one possible way to get that ice cream, 3 scoop? If somebody says and go like, yeah, I guess that would count. Okay, then it is 31 to the power of 3, because how many choices do you have for your first scoop? 31. How many choices do you have for the second scoop? 31. How many choices do you have for the third scoop? 31. So you can have chocolate, vanilla, chocolate. You can have chocolate, chocolate, vanilla. They're all counted differently. Okay, as different. So that's the first question: is with replacement or without replacement? Okay. The second one is, okay, let's say it is without replacement. Okay, so all 3 flavors must be different. Then you have to ask a second question. The second question is, well, if they can be different, does it matter what the order is? In other words, some people say, I can only have chocolate ice cream, but only after vanilla.
What?
Don't ask me why, okay? I'm just making a case here, okay? So let's just say that is the case, okay? Somebody has a taste and go like, I can only have certain flavors, but only after another flavor. So ordering is important. So in that case, we have to consider permutations, okay, where ordering is important. So it becomes 31 for the first choice, 30 for the second choice, and then 29 for the third choice, which turns out to be the same thing as P in parentheses 31, comma 3. Are we good so far? But what if someone says, oh, ordering should not really matter, okay? If a flavor is in one of the 3 scoops, it is in one of the 3 scoops, okay? Then it becomes combination. So then you'll be looking at the permutations divided by 3 factorial. Why divided by 3 factorial? Let's say we are dealing with vanilla, chocolate, and strawberry, okay? How many ways can you arrange those 3? 3 factorial ways, 6 ways. So you have to look at all the six, those six, and say, well, they should be counted as only one because ordering is not important the way I want to count it. So is that answering your question?
Yeah.
And I'm pretty sure in 5 minutes, nobody's going to remember anything about the power, permutation, and combination, but they will remember, I want to go to Baskin Robbins. That's how subliminal message works. They go under the surface, right? The surface in this class is discrete math, but the message underneath is ice cream.
That's the whole point of the class.
No, I'm not getting paid by Baskin Robbins in any way. Yep.
So, when you have permutations, say we're dealing with the same ice cream example.
Mm-hmm.
The first choice you have 31 choices, then the next you have 30, then the next you have 29. With combination, the first choice you have 31 choices, right?
Well, okay, so that's the tricky part of thinking about combinations, because in combinations, first, second, and third do not matter anymore. So you start with permutations, but then you look at all the permutations, you go like, oh, I can see in my permutations, one is chocolate, vanilla, and then strawberry. I see another one here, it's strawberry, chocolate, and vanilla. Oh wait, I see another one here that is chocolate, strawberry, and vanilla. They should be the same, but you will find 6 of them. You will find 6 permutations that contain exactly the same 3 flavors. So you basically say, oh, so if I look at the number of permutations, I should divide it by 6, because for each combination, it manifests as 6 different permutations when you count permutations.
So there's no real right answer to that because you're just dividing it by the factorial.
Right. So the explanation of the equation or the formula for combinations is you have to divide the number of permutations by the factorial of how many items you are choosing. But that's the rationale of that math. So are we good so far with those examples, okay, and the concepts? You good? Okay. So even though the title of the module is counting, sometimes we want to know, give me the entire set of that omega. Instead of give me the cardinality of that omega, give me the actual set. Okay? Now why is that important? Why do you need to know exactly what those possible outcomes are? I'll give you an example. How many people have played the game of Mastermind? It's a decoding or code guessing kind of game. Okay, some people have. Okay, so if you have not, I can show you kind of like an online version of that game. Well, my battery is running pretty low, so probably that. Let's see, what is my runtime? An hour 40 minutes? I'm good. Mastermind game. There we go. So you can look at this. Okay, this is a good. You remember that? The good old days, right? It's a board game. Okay. So what happens is you have I think there are 6 colors to choose from. 6 different types of text to choose from. So what the way the game is played is it's a 2-person game. One person comes up with a combination, and that's why it's on this side, and you can hide it. Okay. The other person will start to guess what the color, what is the permutation of that color. Okay, because ordering is important, and the number of the same duplicate color is actually important too. Okay, so if you have 6 different colors for these pegs, and you have 4 positions, how many permutations do we have with replacement? Because you can have duplicate colors. Well, you have 6 to the power of 4. Okay. So that would be the total number of ways of someone can hide the hidden pattern can be. Okay? But why do you care, about the individual way of arranging these things? Well, because the whole idea of this game is elimination. Okay? You basically start with a random guess. Okay? Whatever you want. You get the clue. Okay? So you can see in this particular case the clue is 1 white peg. 1 white peg basically says you have 1 guess that is of the right color but at the wrong place. Okay? So the second guess, okay, will have to be something that is consistent with the answer to the first guess. Okay. So with the first guess, okay, you run through all of those 6 to the power of 4 ways of arranging the pattern, and you say, well, if this were the actual hidden pattern, would I have gotten this score? Okay, if the answer is yes, keep it. If the answer is no, toss it. Okay, so you're basically using this to eliminate combinations that cannot possibly explain why you got that score. Of the remaining choices, okay? Now, if you don't want to play this game in an optimal way, you just randomly pick another one, okay? So let's say you take this one, okay? And this one, has a score of 1 red peg and 1 white peg, which means one of the pegs you have chosen is the right color and at the right place. That would be this guy here, okay? And one of the pegs that you have chosen is the right color but at the wrong place. So that would be the purple one. Yep. So now you look at all the remaining combinations that can still be possible, and then you further filter using this particular guess and the answer to that particular guess. Go through every single one and say, well, if this were the actual hidden pattern, and these two are my first 2 guesses, would I have gotten those scores? Yes, keep. No, also away. So you're refining, you're narrowing down your choices until you get to the case where you have all 4 guessed correctly. Is that okay? So in a situation like this, knowing, not just counting the total number of ways to arrange things, but knowing the actual arrangements, knowing the actual omega set is important because you're reducing items from the omega set with each experiment. I shouldn't use the word experiment, but with each step, you're reducing the size of that set.
Each trial.
It's not really a trial because it doesn't match our definition of a trial. In a way, yeah. But there's an optimal way to play this game too. If you choose your guesses in a particular way, I think you can guarantee to finish the game in 6 moves or something like that. Where if you do not, you can only finish it in like 7 or 8 moves. So there's an optimal way to play this game. Yep. Yep. It's pretty easy. Yeah, it's pretty easy to do the AI if you don't care about the optimization. If you want the optimization, it gets a little bit trickier because then you have to kind of look at you have to look at the tree thing, right? If I chose this and that turns out to be the right answer, how many more steps do I need? So you need to keep track of that. Yeah, but this is an interesting problem because most computer games, would have the computer generating the pattern, and you be the one guessing because that's an easy one, right? Choosing one of 6 colors and you have 4 positions to choose from, easy peasy. And then you enter your choices and matching it, okay, you first match the ones that have both the right color and the right position, get those scored, okay, take them out of consideration, and then you match the rest that only has a color matching but not a position matching. So that's pretty easy to do too. So most programs, like you can probably download like gazillion apps that can do this game. But flipping it around is not as easy. So you're the one coming up with a combination, you're hiding it from the computer, and the computer is the one guessing it. Okay? Now, since we're talking about this, and we only got like 3 minutes left, it really kind of interesting to help bring this up and connect it with cybersecurity. Okay? You go like, how can you possibly connect this with cybersecurity? Passwords, WEP, okay? What is WEP? It's called Wired Equivalent Protection, okay? Which is the very, very old encryption scheme for Wi-Fi, okay? Should you use WEP today?
No.
Why not? Because it's easy to crack. How do you crack it? You crack it like this, okay? Now, web encryption is 128-bit, okay? The best version of web is 128-bit encryption. So how many ways can you arrange, things? 128 bits, right? 1 bit is a 0 or 1, so it's 2 to the power 128, which seems to be a huge number, right? That's a pretty big number. But when you understand communication protocol, you can now start to eliminate choices. Okay, because as you observe the actual traffic using a sniffer, you can basically go like, no, this is not possible, this is not possible, this is not possible. You basically apply each potential key to decrypt a packet. Once you decrypt the packet, you look at the decrypted version of the packet and goes like, does that make sense? Does it have a frame, the correct place for the frame number, as a lower level physical? Does anyone know the Cisco, not the Cisco, but the stack of network protocols? TCP/IP. Yeah, there's 6 levels, right? Or 5? I cannot remember.
It was like data link and like frame stuff like that.
Right, but at the frame level, where you can sniff, you can actually tell whether a packet makes sense or not. So if a packet does not make sense, that means that cannot be the right key. Throw that away. Okay? This seems to still make sense. Keep it. Okay? But as you accumulate more and more and more packets, you can start to eliminate more and more and more keys. So the idea of cracking web, which is a archaic encryption standard for Wi-Fi, is that. Except you have the computer is hiding 128 of these. Each one can only be a black or white thing because it's binary. And you are trying to apply to these things and go like, does it make sense? Does it make sense? Does it make sense? Until you have enough packets to confirm that, that has to be the only key. Because only this key makes sense for every traffic, every packet that I have sniffed. Isn't that cool? When I started this class, I did not know that I would actually finish the lecture connecting this with web encryption and relating everything back to permutations and combinations. All right, I'll see you guys on Wednesday. Yep.
Couple things.
Yep.